The Atlantic Ocean has long carried a reputation for powerful hurricanes, towering waves, and centuries of maritime mysteries. Yet none of those hazards compare to the immense force hidden far below its surface. Far beyond shipping lanes, cruise routes, and the reach of sunlight lies a place where the Earth's crust bends into one of the deepest scars on the planet. At its lowest point, the Atlantic descends to nearly 5.5 miles, or almost 8,400 meters, into permanent darkness. This is the Milwaukee Deep, the deepest known point within the Puerto Rico Trench, and the deepest location anywhere in the Atlantic Ocean. It is a place where pressure reaches more than 1,000 times greater than at sea level, where temperatures remain only a few degrees above freezing, and where one of the planet's most misunderstood geological systems continues to reshape the seafloor in silence. For decades, much of the public viewed the Puerto Rico Trench simply as another oceanic depression, remarkable mainly because of its depth. Scientists, however, have gradually uncovered a far more unsettling reality. The trench is not merely a deep hole in the ocean floor. It represents one of the most complex and potentially hazardous tectonic boundaries on Earth. Hidden beneath thousands of feet of seawater, enormous slabs of the Earth's crust grind, bend, fracture, and deform under unimaginable pressure. Every movement stores or releases tremendous amounts of energy capable of producing destructive earthquakes, submarine landslides, and even tsunamis that can travel across entire ocean basins. Stretching for roughly 500 miles, or about 800 kilometers, north of Puerto Rico and the Virgin Islands, the trench marks a collision zone between two massive tectonic plates. To the north lies the North American plate. To the south rests the Caribbean plate. These gigantic sections of Earth's outer shell have been moving relative to one another for millions of years. Their motion may appear slow on a human timescale, advancing only a few inches or several centimeters each year, but geological time transforms those tiny movements into continental-scale forces. Unlike the dramatic volcanic arcs seen around the Pacific Ring of Fire, the Puerto Rico Trench hides much of its activity beneath the ocean. That concealment makes it easy to underestimate. Mountains erupting with lava capture global attention. Deep-sea tectonic deformation rarely does. Yet the absence of spectacular eruptions should never be mistaken for geological calm. The Milwaukee Deep occupies the most extreme portion of this trench. Measurements have placed its maximum depth at approximately 27,500 feet, or nearly 8,400 meters. If Mount Washington, the tallest mountain in the northeastern United States, were dropped into the Milwaukee Deep, it would disappear entirely beneath the ocean, with thousands of feet remaining above its summit. Even some of the world's tallest skyscrapers would become tiny specks against the immense walls descending toward the trench floor. Pressure at these depths reaches nearly 8 tons per square inch. Every square inch experiences forces equivalent to the weight of several large elephants standing on it simultaneously. Conventional submarines cannot survive such conditions. Only specially engineered deep submergence vehicles built with titanium pressure spheres or thick composite hulls can safely descend into this hostile environment. Despite the darkness and crushing pressure, the trench is far from lifeless. Specialized organisms have evolved extraordinary adaptations to survive where sunlight has never penetrated. Transparent crustaceans, unusual sea cucumbers, amphipods, deep-sea fish, microscopic bacteria, and other extremophiles thrive within conditions once believed incapable of supporting life. These ecosystems continue to surprise marine biologists because they demonstrate life's remarkable ability to adapt even under immense environmental stress. Yet biology represents only one chapter of the trench's significance. The far greater concern comes from the forces shaping the ocean floor itself. The Puerto Rico Trench exists because the North American plate bends downward as it interacts with the Caribbean plate. Unlike some subduction zones where one plate clearly dives beneath another, the tectonic relationships here are unusually complicated. Scientists describe the region as containing a combination of subduction, strike-slip motion, compression, and extension occurring simultaneously across different segments. This complexity creates an intricate network of faults extending through the crust beneath the Atlantic. Rather than a single fracture, The boundary resembles an interconnected web of faults capable of accumulating stress over long periods before releasing it in powerful earthquakes. Some faults slide horizontally, others move vertically, still others rotate or bend. The result is an environment where seismic hazards become exceptionally difficult to predict. Modern seismic monitoring has shown that earthquakes occur frequently throughout the region. Most remain too small to attract widespread attention, but these smaller events illustrate an important reality. The crust is constantly adjusting. Tiny fractures relieve some stress while transferring additional forces elsewhere. Every movement becomes part of an evolving geological puzzle, extending hundreds of miles beneath the Atlantic. Historical records demonstrate that this region has produced devastating earthquakes before. One of the most significant occurred during the early 20th century. A powerful earthquake struck near Puerto Rico, generating a tsunami that reached nearby coastlines within minutes. Entire communities experienced destructive flooding with little warning. Many residents never had sufficient time to escape before walls of seawater surged inland. The tsunami itself did not require an earthquake rivaling the largest events seen elsewhere around the globe. Instead, underwater landslides triggered by seismic shaking likely amplified the waves. This distinction carries enormous importance because submarine landslides remain one of the least appreciated hazards associated with deep ocean trenches. As tectonic forces deform the seafloor, steep underwater slopes gradually accumulate unstable sediments. Earthquakes need only provide the final trigger. Vast sections of the seabed can suddenly collapse, displacing enormous volumes of water in seconds. Unlike storms, which build gradually over hours or days, submarine landslide-generated tsunamis may arrive with astonishing speed. That reality makes emergency response particularly difficult for islands located close to the trench. Puerto Rico, the Virgin Islands, and portions of the Dominican Republic occupy positions only a relatively short distance from this active tectonic boundary. Depending upon where a rupture begins, tsunami arrival times may be measured in mere minutes rather than hours. Scientists therefore devote considerable effort toward improving seismic monitoring and tsunami warning systems throughout the Caribbean. Understanding the trench also requires examining the unusual shape of the ocean floor surrounding it. Contrary to popular imagination, the Atlantic seafloor is not uniformly flat before dropping sharply into the trench. Instead, the region contains underwater mountains, ridges, valleys, escarpments, sediment-filled basins, and fractured crust created through millions of years of tectonic deformation. These features influence earthquake behavior. They also affect tsunami generation. Even the direction of tsunami energy can change depending upon the shape of the seafloor. Underwater ridges may focus wave energy towards certain coastlines while shielding others. Narrow submarine valleys can channel enormous water masses into concentrated paths, increasing local impacts. This means two neighboring islands may experience dramatically different consequences from the same geological event. Another reason the Milwaukee Deep commands scientific attention involves the bending of the Earth's lithosphere itself. As the North American plate approaches the trench, it begins flexing downward. Imagine attempting to bend an enormously thick steel beam several hundred miles long. Although the movement occurs slowly, the stresses become immense. Rocks that normally appear solid and immovable gradually fracture under accumulated strain. These fractures extend deep into the crust. Water penetrates many of them. The interaction between water, pressure, and fractured rock alters mineral structures, weakens portions of the plate, and influences future fault movements. Researchers continue studying these processes because they directly affect earthquake mechanics. Even today, many aspects remain uncertain. One reason is obvious. Very few instruments can survive permanently at such depths. Deploying equipment to nearly 8.5 kilometers below sea level represents an extraordinary engineering challenge. Every sensor must withstand crushing pressures, corrosive seawater, biological growth, and years of uninterrupted operation without maintenance. Recovering the instruments afterward presents another challenge entirely. Ocean currents, sediment accumulation, and equipment failures often complicate scientific missions. As technology improves, researchers continue placing increasingly sophisticated seismic sensors, pressure gauges, and acoustic monitoring systems across portions of the Caribbean and Atlantic. Each new dataset reveals additional complexity. Some sections of the trench appear tightly locked, storing enormous stress. Others creep slowly, releasing energy through gradual movement rather than catastrophic rupture. Distinguishing between those behaviors remains one of modern geophysics' greatest challenges, because locked faults possess the greatest potential for generating powerful earthquakes after centuries of accumulated strain. The Puerto Rico Trench also illustrates that depth alone does not determine danger. Many people assume the world's deepest trenches automatically represent the greatest hazards. Reality proves far more complicated. Some extremely deep trenches experience relatively limited nearby populations. The Puerto Rico Trench, by contrast, exists close to millions of people living across the Caribbean, with additional exposure extending toward the eastern United States and even parts of the wider Atlantic basin, depending upon the nature of a future event. That proximity transforms geological activity into a matter of public safety rather than scientific curiosity alone. The Atlantic often appears calmer than the Pacific when viewed from the surface. Hurricanes eventually pass, waves settle, shipping resumes. Far below, however, tectonic forces continue operating without pause. Every passing year adds another fraction of movement between the North American and Caribbean plates. Every century accumulates additional strain within buried faults. Every earthquake rewrites part of the geological balance governing one of the deepest places in the Atlantic Ocean. The Milwaukee Deep remains hidden beneath perpetual darkness, beyond ordinary human experience, yet its influence reaches far beyond the trench itself. It represents a reminder that some of Earth's greatest dangers are not announced by smoke, flames, or towering mountains. They unfold in silence beneath miles of seawater, where the planet continues shaping its surface through forces powerful enough to alter coastlines, generate destructive waves, and remind humanity that even the seemingly tranquil Atlantic conceals extraordinary geological power. For scientists, the greatest concern is not that the Puerto Rico Trench exists. Ocean trenches are natural features produced by plate tectonics and have shaped the Earth for tens of millions of years. The concern lies in the fact that the forces operating beneath the Milwaukee Deep never truly stop. Every passing day, the North American plate and the Caribbean plate continue their slow interaction. Their movement measures only a few inches or several centimeters each year, yet over centuries, those seemingly insignificant distances accumulate into enormous strain. Rocks that appear immovable gradually deform, faults become increasingly stressed. Entire sections of the crust bend like an immense steel beam forced beyond its natural limits. Unlike a machine that provides obvious warning before failure, the Earth's crust offers only subtle clues. Tiny earthquakes, slight shifts measured by satellites, changes in seafloor pressure, and microscopic movements detected by highly sensitive instruments all contribute pieces to an enormous puzzle. Scientists monitor these signals continuously, hoping to better understand where stress is building and how it may eventually be released. Modern geodesy has transformed that effort. Networks of global positioning system stations installed throughout Puerto Rico and neighboring islands can detect ground movements measured in fractions of an inch or mere millimeters. What seems like perfectly stable land to the human eye is actually moving continuously. Some areas rise slowly, others sink. Some drift eastward while neighboring locations move westward. These measurements reveal that the entire region is responding to forces generated deep beneath the Atlantic. Satellite radar adds another layer of observation. Using interferometric synthetic aperture radar, commonly known as INSAR, researchers compare repeated satellite images to identify incredibly small changes in elevation across broad regions. Even slight deformation caused by tectonic stress can become visible through sophisticated processing techniques. Together with seismic networks, these observations help build an increasingly detailed picture of the forces shaping the trench. The ocean itself has also become an important source of information. Pressure sensors, anchored to the seafloor, can detect tiny changes in water height that may indicate the passage of tsunami waves across the Atlantic. Unlike surface buoys alone, these instruments measure pressure directly at depth, allowing them to recognize waves that may be almost invisible in deep water, but capable of growing dramatically as they approach shore. That growth surprises many people. In the open ocean, tsunami waves are often only a few feet or less than 1 meter high. Ships crossing the Atlantic may pass directly over one without recognizing anything unusual. The wave's true danger lies not in its height across deep water, but in its extraordinary wavelength, which can stretch for more than 100 miles, or over 160 kilometers. As that enormous wave approaches shallower coastal waters, everything changes. The leading edge begins slowing because it interacts with the seafloor. Water behind it continues moving rapidly, compressing the wave and forcing its height upward. What had been a barely noticeable swell in the open Atlantic may transform into a wall of fast-moving water racing toward beaches, harbors, and coastal communities. The Puerto Rico Trench occupies a position where this transformation deserves careful attention. Puerto Rico, the Virgin Islands, Hispaniola, and numerous smaller Caribbean islands all lie relatively close to the trench. Depending on the location of a major earthquake or submarine landslide, some coastlines might have only several minutes between the beginning of ground shaking and the arrival of tsunami waves. Those short warning times place tremendous importance on public preparedness. Emergency managers repeatedly emphasize that strong earthquake shaking near the coast should serve as its own warning. Waiting for official alerts may consume valuable minutes that simply do not exist. If the ground shakes violently enough to make standing difficult, immediate movement toward higher ground becomes one of the safest responses, regardless of whether a tsunami warning has yet been issued. History demonstrates why this advice matters. The Caribbean has experienced destructive tsunamis repeatedly over the centuries. While none approached the scale of the catastrophic Indian Ocean tsunami of 2004 or the Japanese disaster of 2011, several Caribbean events produced devastating local consequences because nearby coastlines received little advance notice. Many historical records describe the sea withdrawing unusually far before returning with tremendous force. Others describe multiple waves arriving over extended periods, with later waves sometimes proving larger than the first. These observations continue guiding modern emergency planning because tsunamis rarely behave as a single isolated surge. The trench presents another challenge beyond earthquakes and tsunamis. Its steep underwater slopes remain vulnerable to collapse. Submarine landslides occur far more frequently than many realize. Millions of tons of sediment can suddenly break free, accelerating downslope under gravity before spreading across the deep ocean floor. Such events reshape the landscape beneath the Atlantic in ways rarely witnessed directly because they occur under several miles of water. Scientists studying sediment cores recovered from the region have discovered evidence that these underwater collapses have occurred repeatedly throughout geological history. Layer after layer records ancient episodes during which unstable material cascaded into deeper portions of the trench. Some landslides likely accompanied earthquakes. Others may have occurred independently as sediments gradually accumulated beyond their natural stability. Both possibilities concern geologists because either mechanism can displace significant volumes of seawater. The trench also influences regional gravity. Although this effect remains far too small for humans to notice directly, highly precise satellite measurements reveal subtle gravitational differences associated with variations in crustal thickness and the immense depression carved into the Earth's surface. These measurements allow researchers to estimate the distribution of mass beneath the ocean floor and improve models of the trench's internal structure. Understanding that structure remains one of the great scientific challenges of modern geology. The crust beneath the Puerto Rico Trench does not consist of uniform layers stacked neatly upon one another. Instead, it contains fractured rocks, folded sediments, buried faults, altered minerals, ancient volcanic material, and regions that have been compressed, stretched, and twisted over millions of years. Every expedition adds another piece to that picture. Advanced sonar systems now produce remarkably detailed maps of the seafloor. Instead of featureless plains, these surveys reveal towering underwater cliffs, enormous fault scarps, deep canyons, isolated ridges, and massive landslide deposits stretching for miles across the trench floor. Some underwater cliffs rival the height of major mountain ranges on land. The difference is that they remain hidden beneath thousands of feet of seawater. If exposed above sea level, portions of the trench walls would rank among the most dramatic landscapes on Earth. Even reaching the Milwaukee Deep remains an engineering accomplishment. Deep diving submersibles require years of design and testing before attempting such missions. Every bolt, every seal, every viewing port, and every electronic system must withstand pressures capable of crushing ordinary steel like thin aluminum foil. One minor structural failure would prove catastrophic. That reality explains why relatively few human expeditions have ever reached the deepest point of the Atlantic. The darkness itself creates another obstacle. Sunlight disappears within the upper portion of the ocean. Beyond that point lies an environment illuminated only by specialized lights carried aboard research vehicles or by the faint glow of bioluminescent organisms producing their own chemical light. Silence dominates. Temperatures hover only slightly above freezing. The immense pressure compresses everything. Yet despite those hostile conditions, life persists. Scientists continue discovering organisms unlike any previously known. Tiny crustaceans, soft-bodied invertebrates, microbial communities, and deep-sea fish have adapted to conditions once considered incompatible with complex life. Studying these organisms extends beyond biological curiosity. Many possess unique enzymes capable of functioning under enormous pressure. Others produce chemical compounds that may one day contribute to advances in medicine, biotechnology, or industrial processes. The trench therefore represents not only a geological frontier, but also a biological one. Even so, geology continues to command the greatest attention.